So next, let's take a look at the command line. And at this point, I have the layer 3 VPN already set up, where there are BGP peerings. If we were to look at router 2 and look at the show BGP VPN v4 unicast all summary, we see that we have two peerings. We have a peering going to router 5 and to XR1. These are the other provider edge routers, and that we are learning VPN v4 routes from them. So if we are able to get connectivity from a unicast point of view between any of the customer sites, we can assume that the basics of the network are working, like our IGP in the core, our label distribution protocol in the core, the VPN v4 routing exchange for the unicast prefixes. We need to make sure that all of the basics of the MPLS layer 3 VPN are built first before we can move on to any of the multicast routing. So on router 2 then, if we were to look at the show BGP VPN v4 unicast all, we should see that we're learning a bunch of unicast routes from the two different provider edge routers, again, them being XR1 and router 5. So we see that we're learning them in the BGP table. All of them have the greater than sign, which means that they have successfully run the BGP best path selection. So we're going to assume that there's nothing wrong with our underlying layer 3 VPN design. If we were to look at this from the customer router point of view, let's say we were to go to router 7, and let's say we show IP route for the loopbacks of some of the other CE routers, like router 10, I have configured as 10, 10, 10, 10. And we have an IGP route. In this case, we're using OSPF as the PE to CE routing protocol. Likewise, we should have routing information for router 8, which is 8888. Likewise, we're using OSPF as our PE to CE routing. So I should have no problem trying to reach router 8 or router 10. And we can see the individual hops that it's using over the MPLS network. Now, if we were to go somewhere inside the core, let's say router 4, for example, when we look at the global routing table here, we should see that router 4 knows about the core of the network. So it knows about routers 2 through 6 along with XR1, but it doesn't know the details about the customer. So just a standard layer 3 MPLS VPN design here, where any traffic that we want to switch from router 2 to XR1 or from router 2 to XR5, we have to switch this in combination with the transport label that is derived from the combination of LDP and IGP in the core, which we can see from the core if we were to say show MPLS forwarding table. And then the VPN label, the VPN v4 or the VPN v6 label if we were doing IPv6 routing, that's going to come from the BGP peerings between the provider edge routers. But again, the final result is that between any of the CE routers, we have a full mesh of reachability. So there's nothing complex with the route distinguisher policy or route target policy, just a standard layer 3 MPLS VPN design. So then the next step, since we know that now the basic core is working, the basic unicast routing is working, next step would be to turn multicast on in the core. And in this case, this is going to be between routers 2, 3, 4, 5, 6, and XR1. Now, in these implementations with the multicast distribution tree, you technically could use PIM dense mode, but in a realistic design, nobody is going to do that. In the core, it's always going to be PIM sparse mode. The vast majority of the time, it's also going to be source-specific multicast, or SSM. And we'll come back in a little bit and talk about why you would want to use source-specific multicast in the service provider core as opposed to regular sparse mode. But first, we'll look at this with regular sparse mode using rendezvous point assignments. We'll make sure that everything is working. Then we'll switch over to source-specific multicast and see what's the functional difference between the two of these. But again, then the first step is to turn multicast routing on. So on our first router, on the provider edge, router 2, normal multicast configuration. So in global config, we simply say IP multicast-routing. At the interface level, we say IP PIM sparse mode. Now, one key note here about the multicast distribution trays is that on the provider edge routers, whatever the source address is for your VPN v4 peering, which 99% of the time is going to be the loopback interface on the PE. When you are running the multicast distribution trees with protocol independent multicast routing, you need to enable PIM on that interface. So on router 2, in addition to enabling PIM on the LAN interface, which is fast Ethernet 0/0.23, I need to go to my loopback, which in this case is loopback 0, and say IPPIM sparse. Now, you may see in some iOS versions that if you do not turn PIM on, it will give you a warning message saying that the MDT is not going to work unless PIM is on the loopback, but not all of them. So depending on the individual train of code, it might give you a warning to help you out, or it might not say anything, but the end result is that if PIM is not on the interface that's used for the BGP peering, the multicast distribution tree is simply not going to work. So there on router 2, it's basically only 2 commands so far, just IP multicast routing and then IPPIM sparse mode. Same thing is going to be true with the rest of the core. So if we were to go to router 3, here we have IP multicast routing globally. Then on all of the other links, IPPIM sparse mode. Now again, you could use dense mode, you could use sparse dense mode, as long as at the end of the day we can build a multicast tree between the provider edge routers. That's what we're trying to accomplish. So then on 4, 5, and 6 as well. So on global config, IP multicast routing at the link level, IPPIM sparse mode. And then as we're doing this, we want to make sure that there's no problems in the underlying layer 2 transport. So once you configure PIM, you want to look at the show IPPIM neighbors and make sure to check this from both ends of the link. There can be certain cases where the PIM neighbor shows up on one side, but it does not show up on the other. So do yourself a favor and just go to both sides, look at show IPPIM neighbors, make sure the address is listed there, and then you can move on. You could also look at the show IPPIM interfaces to quickly see, did you actually enable PIM on the interfaces that you need? For the devices in the core, like router 4 here, who is just a P router, you technically don't need to enable PIM on the loopback. In this case, it is on the loopback. It's just kind of a best practice to make sure you don't leave it off. It's not going to give you any advantage here, but it's not at the same time gonna hurt. So then on router 5, likewise, IP multicast routing. On the loopback, we need PIM because this is a PE router, so IPPIM sparse. Then on the LAN interfaces facing towards the core. Now, I'm not yet going to turn it on the interface that faces towards the customer, which in this case is fast Ethernet 1/0, where here I have VRF-A configured, because at this point I did not turn the multicast routing process on for that individual routing table. By saying IP multicast routing, I'm only turning it on for the global table. I have not yet turned it on for that particular customer table. So again, once I know that everything is working in the core, then I'll come back, turn it on for the customers table. So next on router 6, same config, IP multicast routing. Then on the interconnects between the core, IPPIM sparse. So here we have those 3 subinterfaces. Then lastly, we have the iOS XR instance. So as we know, the syntax is going to be different on iOS XR, but the logic is going to be the same. You'll see that most of the configurations for multicast routing are pretty self-explanatory in iOS XR if you were to take a look at the documentation. The main goal we need to do is just to make sure that PIM is on all of the interfaces that we are doing our IGP routing on in the core. The vast majority of problems you'll run into with multicast routing is that if you have some interfaces that are running PIM and IGP, and other interfaces that are running IGP without PIM, or other interfaces that are running PIM without IGP. That's where the vast majority of the reverse path forwarding, or the RPF errors, are going to be in the network. But as long as your IGP and PIM is on a one-to-one basis, then we're not going to have any problems with that. And in iOS XR, they make this problem even easier to solve by simply, when you enable multicast routing, you just do it on all interfaces at the same time. So in global configuration, we go to the multicast-routing mode. We specify, are we doing this for IPv4 or IPv6? So the address family, in this case, we're doing IPv4 multicast routing. And then what interfaces do we want to turn it on? Now, technically, this is separate from the PIM process, that there is a separate router PIM mode that you can selectively change the individual PIM attributes, turn it on or off an individual interface. But by default, if you turn multicast routing on the interface, it's automatically going to enable PIM for you. So I could specify the individual links. Like in this case, I could say interface gig 0/1 00.619. But the shortcut for this is simply to say interface all enable. Because again, in the vast majority of designs, for all interfaces, you're already going to be running IGP. And to make sure you're not going to run into any reverse path forwarding problems, you want to run multicast on all of those interfaces as well. Now, additionally, we need to tell the multicast process when we're originating the multicast distribution tree, what is the source interface that is going to come from. And now, in the case of regular iOS, we'll see when we configure this under the VRF level, it's automatically going to inherit what the BGP update source is, or essentially the VRF source interface for that particular VRF. But in the case of iOS XR, you do need to specify this. And this is going to be the MDT source interface, which in this case I'm going to say is simply my loopback, because that's where my BGP peerings are being sourced from. So if we look at the show config, up to this point, outside of the scope of the MDT, because we'll come back to this on the other routers, it's basically only 3 commands where we're enabling multicast routing globally, specifying what is the address family, and then turning it on the interfaces. Now, once we commit this config, ideally what we should see is a log message on the other router that now the PIM adjacency is up. So if we look at the show IPPIM neighbors, this is on the regular iOS side. We see that we have the other iOS routers, which are router 3 and 5, but then we also see we have the adjacency with the iOS XR instance. From XR, if we were to look at, instead of the show IPPIM, the verification is going to be show PIM. So if we were to simply say show PIM neighbors or show PIM interfaces, this is going to tell us who are we adjacent with, where the asterisk here, this means that this is the local process. So you can basically ignore these ones. It just means that PIM is running on the interfaces that have those addresses. This is what you're looking for. Who are the actual other routers that you're adjacent with? So here it says I'm adjacent with 20.6.19.6. This is router 6's address. If you were to have a problem with this, when you look at the show IPPIM interface, you need to make sure that PIM is on. So if multicast is enabled, but PIM is disabled for some reason, it's going to say that PIM is off. But simply, when we look at the show run multicast, since I said that all interfaces are enabled for multicast routing, it's automatically going to turn PIM on for all of them. So you can selectively do it, but this is going to be the way just to grab all of them at the same time. So at this point, we have PIM sparse mode configured on all of the routers. Just to double check real quick, let's go back through here. Router 6, we should see it has 3 neighbors. It has router 3, has router 5, and XR1. Router 3 likewise should have 3 neighbors. If we show IPPIM neighbors, should be router 4, router 2, and router 6. Then router 4 and 5 should have 2 neighbors. We see 4 is adjacent with 3 and 5. 5 should be adjacent with 4 and 6. Then lastly, 2 should be adjacent with 3. So just a quick verification, make sure you don't exclude this from your normal process. Because if you accidentally left the command off one of the links, you don't want to waste an hour troubleshooting the tunnel of the multicast distribution tree and then figure out that you just had PIM off on one of your interfaces. So now at this point, PIM is on in the core. We're running PIM in sparse mode. And since we're not running source-specific multicast, we know that this means we need to have a rendezvous point assigned. Now, how we do this, the design of the rendezvous point assignment, it's independent of the multicast VPN configurations. So we could be doing this statically. We could be doing this with AutoRP. We could be doing this with Bootstrap router. We could also be doing Anycast with any of those three combinations. Doesn't really matter. As long as everyone agrees who is the rendezvous point and that we can build our shared trees and our shortest path trees, this is what we're really concerned with. So in this case, for simplicity, I'm simply going to use BSR because it means that there's only two commands that I need to issue in the design. I need to specify who is the Bootstrap router and then who are the rendezvous point candidates. And these could be the same device or they could be separate devices. It doesn't really matter. As long as everyone agrees on this, that's going to allow them to build the shared trees for the star comma G's and then the shortest path trees for the S comma G's. So let's say in this case that it's going to be router 4. We're going to configure this as our rendezvous point and it's going to be the BSR. So on router 4 in global config, this is just going to be two commands. We'll say IPPIM BSR candidate, and what's the address that you want to announce. In this case, I'll use my loopback, and then IPPIM RP candidate from the same interface. Now, in this case, it does mean that I would have to enable PIM on the interface that I'm advertising the BSR information from. Same would be true if we were doing AutoRP. So whatever the interface is that you're sourcing the candidate RP announcements and the mapping agent announcements, you would have to have PIM enabled on that particular link. Now, if PIM sparse mode in the core is working up to this point, I should simply be able to go to all of the routers in the core and now look at the show IP PIM RP mappings. And if everyone now agrees that the rendezvous point is router 4, that this information came from router 4, who is the BSR, then we know that the next step of the core is working. That everyone agrees who is the rendezvous point. Now we know where to send our register messages. We know where to send our join messages. This is going to allow us to build both the shortest path tree and the shared trees. Now from iOS XR, we do not use the show IPPIM RP mappings. Instead, we use the command that's similar to IPv6 multicast routing in regular iOS, which is the show PIM range list. And another change here is instead of saying show IPM route, when we're looking at the actual trees, this is going to be the show PIM topology. So show PIM topology is the equivalent of show IPM route. The show PIM range list, this is the equivalent of the show IPPIM RP mappings. But we can see here that the XR instance does know through BSR that the rendezvous point is 4444 and it's for the entire multicast range, which is 224.0.0.0/4. So now at this point, everyone agrees that we are running multicast routing, we are running sparse mode, and we agree on who the rendezvous point is. Now, if I wanted to test this a little bit further, I could try building a tree from the receiver back up to the rendezvous point and building a tree from the sender to the rendezvous point. So let's say in this case that I now want to make, let's say router 6, I'll make this a receiver. So to do this, I could simply go to any interface on router 6 that's running PIM, and at that interface level, let's say this subinterface that points to XR1, and we'll say IP IGMP join, and then any address that's in the entire multicast range, because we're not filtering which groups the rendezvous points are assigned to. So let's simply say 224.111. Now, if this is working, what we should see is that on the reverse path from router 6 back to the rendezvous point, everyone should now have the star comma G entry for the 224.1.1.1. So on router 6, if I were to say show IP route for 4444, which is the rendezvous point's address, it says my reverse path is going to go to one of these two interfaces, because in this case there's equal cost matches between the two of them. If I were to say show IP RPF for the address, it says in this case the RPF interface is fast Ethernet 0/0.56, which means that if I were to go to this RPF neighbor, which is router 5, and if I were to say show IPM route for 224.111, what I should ideally see is that there is now going to be a star comma G entry for star comma 224.111, wherein the outgoing interface list, or the OIL, is going to point from 5 down to 6, and the incoming interface is going to be fast Ethernet 0/0.45, which is the upstream interface pointing towards the rendezvous point. Because for the shared tree, which is the star comma G, the root of the tree is the rendezvous point, and everyone is going to be downstream from the RP. So on router 5, if we were to say show IPM route 224.111, I ideally should see that star comma G, where the incoming interface FA 00.45, then outgoing interface is down to router 6. This is telling me that my PIM join message was properly processed by router 5 as it's going upstream towards the rendezvous point. Then likewise, if I was to do the same thing on router 4, show IPM route for 224.111, I should see that the incoming interface is null because I am the root of the tree, and the outgoing interface is going to be whatever I'm using to reach router 6. So router 4 is the root of the rendezvous point tree, the RPT, or the star comma G tree, with the outgoing interfaces pointing down to 5, then from 5 it's pointing down to 6. So this at least tells me that everyone knows who the rendezvous point is and they know the reverse path in order to reach it. Now the second portion, which is to test the actual senders, this can be a little bit more difficult in some of these designs because from a practical point of view, the router is not going to be the source of the multicast feed. You're always going to have some end application, like maybe an IPTV server or some sort of media server that's actually generating the UDP feeds. And where this can potentially become an issue is when the router is trying to do the registration with the rendezvous point. Where normally what should happen is that when the multicast feed is received on the router that's running PIM, that's running multicast routing, it's going to receive this message in on the interface. It's not a control plane message, it's just multicast packets in the data plane. It's going to receive these in, and it says I need to register them with the rendezvous point, or basically tell the rendezvous point that I have a sender. Now, when we're doing this from the router itself, you'll see that depending on who is in charge of the registration, which is the job of the designated router, you need to initiate the packets from the device that is not the designated router. Because the multicast has to be coming in on the interface that is assigned as the DR in order to actually trigger the multicast registration. So if I were to look at router 2 and look at the show IP PIM neighbors, in this particular case, router 3 was elected the designated router for this segment simply because its IP address is higher than router 2. But if these roles were swapped, where this here was router 2 and this here was router 3, or even simpler if their IP addresses were swapped, then you might have a problem when you're trying to originate the packets from this side. So you'll see when we get to the customer testing, one of the ways that you can fix this problem is to change the designated router priority, where the priority is 1 by default, which means it's going to use the higher IP address as the tiebreaker. But you can change the priority higher to be more preferred, or if you were to change it to 0, it means that device is not going to participate in the election. But ideally, what should occur when you send multicast packets out, let's say we send a normal ping, if I were to ping, and I'm going to do an extended ping, let's ping 224.222, and I'll send just one packet. That should be enough for the registration. Extended commands, yes. I want it to go out this specific interface, which is fast Ethernet 0/0.23, and it's coming from 20.2.3.2, which is my address assigned on that link. Now, if the registration was correct, what should happen is that when the ping comes from router 2, and let me revert that back. So it's coming from router 2, the ping goes out, and it's received in on the interface that is assigned as the designated router. And if this is working properly, what we should see is that router 3 is going to then tell the rendezvous point, which in this case is router 4, with a unicast register, basically that I know about the sender. I know about now a specific S, G entry. So on router 4, if we were to go to router 4 and look at now the show IPM route for 224.222, we should see that there is an S, G entry. Now, simply based on the fact that router 4 knows about who the sender was, this means that the registration was correct. So router 3 did actually generate that message telling the rendezvous point there's this particular sender sending packets to this particular destination, where these two together, this is making up the S, G pair, or the source and group address. So then if there weren't any receivers for 224.222, we could build the actual tree. But the key is that these two steps separately, the join that originates from the IGMP report from the receiver, gets turned into the PIM join, goes upstream towards the rendezvous point. That's what's used to build the shared tree, or the star, G tree. Then on the sending point, we have the multicast traffic that's coming in unsolicited from the actual source. That's eliciting the PIM register, which is the unicast message going to the rendezvous point, telling them I now know about this S, G. And since the rendezvous point knew about both of those portions that we looked at, the 224.111 was the star, G, and then the 224.222, that was the S, G, I now know that inside of the core, PIM sparse mode is working. If there was any kind of complex routing in the core, maybe some links running IGP and some links not, or maybe MPLS traffic engineering that could potentially have a negative impact on the building of the multicast trees inside of the core. Now, as a side note here, as I mentioned this with MPLS traffic engineering, since an MPLS TE tunnel is a one-way tunnel, where to go from point A to B, you have to build a tunnel from A to B. Then if you want to go from B back to A, you need a separate unidirectional tunnel. It doesn't behave like a normal GRE tunnel or a normal IPsec tunnel. This means that you cannot run routing protocols on top of it. Or furthermore, it means that you cannot run PIM on top of it. So if you have a TE tunnel and you're running multicast routing, there is going to be a problem with the reverse path forwarding over the tunnel. So in order to avoid this problem, you could do a static multicast route, or you could run a multicast BGP, but for whatever protocol you're running in the core of IGP, so either OSPF or IS to IS typically, you simply go under that routing process and you say MPLS traffic engineering multicast intact. So what this says is that if you are running PIM and you are running TE, and your reverse path forwarding check points to the TE tunnel, assume that the check passes. So instead of having to do a manual multicast static route to override the tunnel, this is telling the router there's an exception because on the TE tunnel you cannot run PIM. So if the RPF check points to the tunnel, assume that that is supposed to be there, and then you're just going to allow the RPF check to pass. But otherwise, as you're testing the core of the service provider network, if there's some problem with the trees being built, it means that your multicast distribution trees down to the customer are not going to work. So now up to this point, we have the core of the service provider multicast working, where configuration-wise, it's very straightforward. We just turn multicast routing on. Then at the interface level, we have IPPIM in sparse mode, and then we configure the rendezvous point. Or again, in this case, I did that with Bootstrap Router, but you could as easily have done it with AutoRP or with static assignments. Now, the next step then is to turn multi-guest routing on towards the customer. Now, from the customer's point of view, which in this case is going to be 6 different routers here, which is router 1, 7, 8, XR2, router 9, and router 10. From their perspective, this is just normal global multi-guest routing. So it's essentially the same configuration that we did in the core. If I were to go to router 1 and let's say show run include interfaces or PIM or multicast, there's nothing special about this config. So I already have multicast routing configured. At the interface levels, I have PIM in either sparse mode, dense mode, or sparse dense mode. If you're running some variation of sparse mode, then likewise you need a rendezvous point assignment. In this case, I'm doing it with BSR. Router 1 is both the RP and it's the Bootstrap router. Now, as long as on the customer sites they all agree on what their topology is supposed to be, that's going to be the next piece of the puzzle. So if I were to go to router 7 and say show IPPM neighbors, I need to make sure I'm adjacent with router 1. Likewise, if I were to go to router 8, show IPPM neighbors, I need to be adjacent with XR2. On XR2, if we look at the show run multicast, it's basically the same config that we had on XR1, which is just to turn multicast routing on. Go to the address family, in this case it's talking about the IPv4 multicast routing process, and then enable it on the interfaces. You'll see that most of the examples also have these 2 commands, which is the rate per route and the accounting per prefix. What this allows you to do is to generate hits on the counters for multicast forwarding, even though the forwarding is happening in hardware. Because we know with some of the lower level platforms like the ISRs or ISRG2s, they're doing their forwarding in software. They're running Ceph in software. But in the case of the higher level platforms like the 7206VXR, or in this case the GSRs or higher, they're running this in the hardware implementation. So it makes it a little bit more difficult to track down either through debugs or through some of the counters exactly what's going on. So then once we have this enabled, we can look at the show mfib for the multicast forwarding information base, show mfib route rate, and show mfib route statistics, where these 2 outputs, these would be similar to in regular iOS if we were to look at the show IP mroute count, which is going to show you the individual source and group pairs, the S, Gs, and how many particular packets are being forwarded or are packets being dropped, and then what is the particular reason. So once we get to the point that we actually have multicast senders and receivers in the network, this is a good quick way to see, is the traffic actually forwarding? And if it is not forwarding, what is the particular reason that it's not forwarding, or why is it getting dropped? So again, you don't necessarily have to use those 2 commands, the rate per route and the accounting per prefix, but it doesn't hurt to add those in just in case you want to look at the counters and see, are your S, G pairs actually working? So now up to this point, we have all of the PIM adjacencies working between the customer sites. So router 1 is adjacent with router 7, 8 is adjacent with XR2, router 9 is adjacent with router 10, but we don't yet have any communication from the customer edge to the provider edge within the scope of multicast. So now our next step would be on the PE routers, which again are routers 2, 5, and XR2, to enable the VRF-aware PIM process to form our PIM adjacencies with the customers, and then ultimately what is going to allow us to form the MDT, the multicast distribution trees between the PE routers, and then actually forward the traffic between the customer sites. Now, in the case of regular iOS, this configuration is pretty straightforward. The only thing that we're changing is that we're using the VRF-aware commands for PIM as opposed to the regular commands. So if we were to go to router 2, our next step then, just like in regular multicast routing, we would normally say IP multicast routing in global config. In this case, we need to turn it on for that individual VRF table. So we say IP multicast routing VRF A. Now, from this point on, if we were to do any type of rendezvous point assignment or maybe BSR or AutoRP that is specific to that individual routing table, we need to make sure that we're using the individual VRF aware commands. So things like the IPPIM, RP address for the particular VRF. And you'll see that if you use the question mark through a lot of these commands, the VRF sometimes comes in the middle of the command, sometimes it comes afterwards. So you kind of have to just fumble around to figure out for that particular configuration command or that show command, where exactly does the VRF get referenced. So here we would say IPPM VRF A, what's the RP address, or what's the BSR's address. So the same type of logic as the global routing table, we're just doing it for that individual VRF table. Now, at the interface that's actually running the VRF, which in this case is Fast Ethernet 1/0, there's no special config here. We just have VRF forwarding, and then we're going to have IPPIM in sparse mode at the link level. So we should see now, once this is configured, we have the PIM adjacency come up, but specifically it is inside the VRF. So it says the PIM neighbor is up in VRF A. If we were then to look at the show IPPIM VRF A neighbors, we see that we have the adjacency with router 1, and then we need to do the same thing on router 5, on the PE to CE link to router 9, and then also on XR1 on the PE to CE link to XR2. So next on router 5, we need to say in global config IP multicast routing for VRF A. At the link level then, IPPIM in sparse mode. Then on XR1, it's going to be a similar configuration to what we had on XR2 if we look at the show run multicast. We're enabling all of the interfaces that are in the VRF, specifically for the address family IPv4 under multicast routing, but this is then going to be under the VRF. So globally, we would say multicast-routing for VRF A. What are the interfaces that we want to enable? So I'll say interface all enable, which again, I could be specific. I could say just enable it on packet over SONET 0600. In this case, there's only one link in the VRF, so it's not going to make a difference. By doing this, it's just saving you that trouble that if you do have additional interfaces later, you want to make sure that your PIM is enabled on a one-to-one basis along with your IGP routing. So similar like in LDP, where you have the LDP auto config under your routing protocols, you want to make sure that LDP and IGP is on a one-to-one basis on the interfaces. Same logic here we want to use for PIM, because that's going to avoid the vast majority of the problems with the reverse path forwarding failure issues. So once we commit this config, we should see that we're going to have a PIM adjacency that is going to come up with XR2. So here, if we look at the show PIM neighbors, this is going to show us our global neighbors. We can see we have the adjacency with router 6. If we were to say show PIM for VRF A neighbors, we see now we have the adjacency with XR2. So just like in regular iOS, it's keeping two separate tables. One is going to be for the global table, and then one is going to be for that individual VRF. The same is going to be true for the actual multicast routing table. So when we go to any of the PE routers like router 2, and we look at the show IPM route, this multicast routing table is talking about the core of the SP network. This is the equivalent to the show IP route. It's essentially the global multicast routing table. Then if we were to look at the equivalent of the show IP route VRF A that's talking about that individual customer, we would have to say show IPM route for VRF A. And this is important to keep these two tables separate, the logic of the verification, because there's different types of information that we need to look for inside of the VRF versus inside of the global table. So now at this point, we have the PIM adjacencies from the provider edge to the customer edge. On router 2, if we were to look at the show IPPIM for VRF A, the RP mappings, what we ideally want to see is that router 1 is going to be the rendezvous point for that particular VRF. So on router 1, if we look at the show IPPIM RP mappings, it says that This system is a candidate RP. Let's say show run include PIM. It is a PIM BSR candidate on its loopback 0. It's an RP candidate on its loopback 0. And let's look at on the loopback, we don't have PIM enabled. Okay, so again, this is one of the common mistakes that you could make either on anywhere in the core you're running multicast. If you're using your loopback as the rendezvous point address, you need to make sure that PIM is on that interface. So if we say IP PIM in sparse mode, and then also once we enable the MDTs on router 5, router 2, and XR1, we need to make sure that PIM is running on whatever the update source is for BGP, which typically is going to be your loopback interface. But now on router 1, if we look at the show IP PIM RP mapping, we should ideally see that router 1 is going to be the rendezvous point. If we look at this on router 2 as well, we should see that eventually we're going to learn about router 1 here. So as I mentioned, some of these versions will give you error messages that say, like you're trying to run BSR on your loopback, but you don't have PIM on the loopback, but not all of the versions are. So just double check that you have PIM enabled there. It's not going to hurt anything if you turn it on and you don't actually need it. Okay, so now we can see inside of the VRF, we know that router 1 is going to be the rendezvous point for the customer routing. Now, at this point, we don't yet have any of the tunnels built from 2 to 5 or from 2 to XR1 or from 5 to XR1, which means that the other customer routers like router 8, XR2, router 9, router 10, they are not yet going to know that router 1 is supposed to be the rendezvous point for their individual topology. So on router 9, if we were to look at the show IP PIM RP mapping, we see that we do not know that router 1 is a rendezvous point. Once the MDT tunnels are working and the transit over the service provider network is successful, we then should see that everyone agrees inside of the customer network that router 1 is the rendezvous point. And that's a quick verification we can do, just show IP PIM RP mappings and make sure that router 1's loopback does appear there. So then our basically final step here is to turn the MDT tunneling on the PE routers, and then this is going to tie this entire design together. Now in regular iOS, this configuration is really straightforward. On router 2 and router 5, if we were to look at the show run section router BGP, essentially any of the neighbors that you have activated as VPN v4 neighbors, these are the ones that you're going to want to turn on the MDT address family. Now, of course, if you have other customer VRFs that are not running multicast routing, you wouldn't necessarily need to activate the MDT to those PE routers. But if all the PE routers are also servicing VRFs that are doing multicast routing, then likewise you would want MDT activated everywhere. So you can essentially take this syntax here and just change it around a little bit. Where as opposed to saying address family VPN v4, we'll say address family IPv4 MDT. We want to activate the neighbors and then also send extended communities, which is going to allow us to have backwards compatibility with some of those older code versions that didn't have the address family MDT. So it's not really 100% required, but really there's no reason that you would not send the extended communities to them. So under the BGP process, activate the MDTs. We should see now that the BGP neighbors are going to go down and stay down because we're trying to, during the capabilities exchange, trying to negotiate an address family that's not yet supported on the other side. So we see it says router 5 is removed from the topology base because a BGP notification was received. Basically, this means that router 5 doesn't yet have the MDT configured, which in this case is 2/8. So it's IPv4 unicast, but for the MDT routing. Okay, so if we go to router 5, then show run section router BGP. Basically, the same change here on router 5. We're taking what was our VPN v4 address family config. This is turning into an IPv4 MDT address family. And what we should see once this is enabled, so under BGP, address family MDT, we should see that router 2 and router 5 form a PIM adjacency inside of the VRF, but over this GRE tunnel interface. So if we were to look at the show IP PIM neighbors, we know that router 5 and router 2 physically here, they're not directly connected. So it doesn't make sense that in the global routing table that 2 and 5 would form a PIM adjacency. But inside of the VRF, we now essentially have a GRE tunnel that is formed between them. And the tunnel is part of now VRF A. And once this tunnel is up, then we're going to be running PIM over this. So there's no specific configuration you need to do in order to turn the tunnel on, just as long as they're running the MDT address family and that they are going to agree on what is the MDT's address, which is our next step to list what's the actual multicast group address that we're going to be using. Then we should see that they're going to form the adjacency, and then ultimately that the traffic can be tunneled over the SP network. So on router 5, if we were to look at the show IP PIM VRFA neighbors, once this is finally working, not only should we have a PIM adjacency with the customer routers, but we should also have PIM adjacencies with the other PE routers that are part of that particular VRF routing for multicast. So then our next step would be on XR1. If we look at the show run multicast, we have the address family enabled for both VRFA and for the global routing table. Next step then is under the BGP process to turn the MDT on. So if we show run router BGP, basically the same config that we have here that's activating the neighbors for VPN v4, we're now going to do this for IPv4 MDT. So address family IPv4 MDT is going to be enabled globally. Then router 2 is an IPv4 MDT neighbor, as is router 5. So this is just allowing them to negotiate that capability that again is going to encode their loopback address and the particular group that they're using for those individual tunnels. It's basically allowing them to advertise what is the S, G pair. So once we commit this config on XR1, then we have one final step, which is to tell that particular VRF what's the actual group address that we want to use. Now there's two different ways to configure this. One is the MDT default address, and one is the MDT data address. So first I'm going to go through the MDT default. We'll look at it working that way. Then we'll look at why you would want to use the MDT data and why you would want to use source-specific multicast for this implementation as opposed to just regular sparse mode. So then our last step, if we look at the show run section VRF, under VRF definition A, under address family IPv4, we need these routers to agree what's the multicast address you're going to use for the tunnel. And this is the MDT data or the MDT default. So the default one here, it's any arbitrary address as long as they agree on it. So I'll say 239.0.0.1. So router 5 is going to have pretty much the same exact config. Then on XR1, this is going to go under the multicast routing process under the VRF. So if we look at the show run multicast, this is going to go here under VRFA inside multicast routing. So on VRFA, we say what is the MDT default address, or what's the MDT data address. Here the default, I say, is 239.0.0.1. Again, as long as they agree on what this is, that's what we're trying to match here. So once this config is committed, this then should be the final step for everything working. If we were to look at router 2 and router 5, we should see now that we're going to have PIM neighbors over these tunnel interfaces. So if we say show IP PIM VRFA neighbors, once everything is finally converged, and that the routers learn about each other's S, G pairs and actually join those multicast feeds, then we can have the PIM adjacencies, and then we can have the actual forwarding over the service provider core. Now, there's two separate verifications we need to do in order to make sure that this is working. The PIM neighbors are going to be inside of the VRF. So the tunnel itself is servicing the VRF, but the forwarding of the tunnel is going to happen inside of the global routing table. So again, the PIM neighbors, we want to make sure that these are inside of the VRF, but when we look at the actual data plane, this is going to be in the global multicast routing table. So we want to verify by looking at the show IPM route, do we know the S, G pairs for the other PE routers? Where in this case, I'm learning about 19, 19, 19, 19, which is XR1. I also have my own address, 5555, but I do not yet have 2222, which should be the MDT source address of router 2. Now, it's possible that this is still converging, so we'll come back to this verification in a second here. But at a minimum, what this is telling us is that router 5 has joined the MDT tree for XR1. And notice if we look at the flags, it says that I am on the shortest path tree, which is the T, for this particular S, G pair. So the traffic does not have to route through the rendezvous point in order to get there. But I do know that there is a rendezvous point, which is router 4. Because we're running regular sparse mode here, we're not running source-specific multicast. It means that if we were to go to router 4, who is the rendezvous point, and we look at the show IPM route, we need to make sure that all of those senders have registered their addresses with router 4. So ideally, router 4 is going to know about all of the S, G pairs. It should be 2222, 239.001, 5555, and 1919, 1919. At least during the initial registration process, it's going to have to know about all of these senders. So now on router 2, let's look at this here. If we were to say show IPM route, it says I do have the MDT tree, which is 2222, going to 239.001. If we look at the show IPPIM RP mappings, I want to make sure that I know who the rendezvous point is, and this should allow me to do the registration with them. So we see our own address, but we don't see the other ones. So at this point, assuming that the other configuration steps were correct, that if we show run section VRF and we show run section BGP, that we have multicast routing on, we agree on what is the MDT address, we have the MDT address family activated, then the step that is probably missing here is to make sure that PIM is on the correct interfaces. Where again, since here under the BGP process, I am sourcing my BGP peerings from the loopback, I need to make sure that PIM is actually on this interface. So on router 2, let's look at the show run interface loopback 0. And actually that's what the issue is here, that the PIM is not enabled yet on the loopback. So it's a really tiny mistake, but it can be very costly in the exam or just in a real implementation if you're trying to troubleshoot why this is not working. You need to make sure that PIM is running on that link because that's where we're sourcing the tunnel from. So let's double check this on router 5 as well. Show run interface loopback 0. Likewise, we don't have PIM on there. On XR1, that was not an issue because when the global multicast process was turned on, it says interface enable or interface all is enabled, which includes the loopback that we're using as our update source for BGP. So now if we look at router 2 and router 5, we should see that we have now PIM adjacencies that are occurring over these tunnels. So this is now the multi-point GRE tunnel that is going to be between the PEs. So ideally, we should see the peering up to 1919, 1919, which is XR1, but also to 5555. If we look at the show IPPIM VRFA neighbors, we see we do have an adjacency with XR1. If we now show IP mroute in the global table, again, we need to make sure that we have the S, G pairs for all of the other PE routers. And we see there's another log message there that router 5 is a neighbor. So we should be seeing all three of these. That I know that router 5 is a sender to 239.0.0.1. I know that I'm a sender to 239.0.0.1, and we know that that XR1 is as well. So again, this is essentially what is being encoded inside the BGP address family. What is going to be the source address of your feed, and what's the destination address, or what's the MDT address. We can also look at this, the specific BGP information, if we were to look at the show IP PIM MDT BGP. This tells you who are the devices or the other PE routers that are participating in that particular multicast distribution tree, which in this case is for the address 239.0.0.1. Router 5 is advertising itself with this particular next hop. Basically, it means that this address is then going to be the source of that group pair, where the S, G would then be 5.5.5.5, 239.0.0.1. Now, if we were to go anywhere inside of the core of the network, let's say on router 6, for example, router 6 should now know the S, G pairs for all of those PE routers that are sending traffic to that particular group. So on router 6, if we go to the global table and say show IP mroute for 239.0.0.1, we need to make sure that all three of these entries are in there. That we know about 2222, we know about 5555, and 1919.19.19. So right now, these should be shortest path trees, which it is. The flag capital T means it's on the shortest path tree, or the SPT, and the actual routing is then going to be based on your underlying IGP. So again, as I mentioned before, this is kind of a hack on the process, because the actual multicast traffic is not being label switched, because we don't have labels that are pointing to multiple destinations at the same time. We don't have those multi-point or the multicast label switch paths. We're just using the logic that we already have these VPN v4 BGP peerings, so we're just adding on top of it the encoding of these S, G pairs, and then using GRE plus the global multicast routing table in order to actually get the traffic from point A to point B. So now at this point, once the tunnels are actually formed, now we can go to the final customers and look at the verification. Where previously on router 1, we saw that this was the candidate RP and this was also the BSR. Router 7, who is on the same site as router 1, when we look at the show IP PIM RP mapping, it should already know that router 1 is the rendezvous point, because these two routers, they're directly PIM adjacent. But if we were to go over to router 8 and look at the same thing, the show IP PIM RP mapping, if it knows now that router 1 is the rendezvous point, it means that it had to have learned that over the SP network, that there was the PIM message that was going between 8 and XR2, where PIM is encoding that BSR update. Then we have the CE to PE PIM relationship between XR2 and XR1. Then we have over the MDT tunnel, PIM running between XR1 and router 2, and then this is tying together the PIM relationships on the other customer sites. So this then is our next verification. Since router 8 knows through BSR that router 1 is the rendezvous point for the customer network, it must mean that the MDT tunnel is working between the PE routers, because otherwise the PIM messages would not be able to be exchanged. If we were to go down likewise to router 10, show IP PIM, RP mapping, if we know that router 1 is the RP, it means that the tunnel is working. If we were to go to XR2, same type of logic. Instead of saying show IP PIM, RP mapping, we're going to be saying show PIM range list, where it should say that the address 1111 is the rendezvous point for the entire multicast range, 224.0.0.0/4.